Hello, my name is William Beach. This is for class CDA4240C, Lab 3. In this lab, we design an ALU and we program it using Vivado and VHDL. Gone ahead and programmed my FPGA and labeled it. A and B are 6-bit inputs. They are represented by these 6 switches from least to most significant bit and from least to most significant bit. Our select selects which component of our ALU we'd like to use. There's 4 different components. There's an adder, a multiplier, a logic unit, and also a shifting unit. And since there's 4 bits for our select, there's 16 possible combination outputs depending on our A and B input. And then our R right here actually denotes our output. And it's represented by 6 LEDs, and it's a 6-bit vector output. So I'll go ahead and run through the combinations. So for our first set of inputs is going to be A is going to be 4, which is going to be 0, 0, 0, 1, 0, 0, and B is going to be 2, which is 0, 0, 0, 0, 1, 0. And select is going to be 0, 0, 0, 0, which is the sum with no carry of A plus B. And this is going to be 6. And as you can see, from least to most significant bits in our 6-bit output, we have 0, 0, 0, 1, 1, 0 from most to least significant bit, and thus that is the value of 6. Going forward for the next combination for select is 0, 0, 0, 1, and this represents the carry of A plus B, which is 0, and as you can see, this is 0, 0, 0, 0, 0, 0. And then for our next combination, it's going to be, for our select is 0, 0, 1, 0. And this represents the difference between A and B without a carry. So A minus B, which is 4 minus 2, which is 2. So as you can see, we have 0, 0, 0, 0, 1, 0 in our LEDs, which represents 2. And then our borrow of A minus B is represented by 0, 0, 1, 1 in select. And as you can see, our borrow is 1. 0, 0, 0, 0, 0, 1. And then for our next set of combinations, A times B, since they're both 6 bits, our maximum output of bits is 12 bits, 2 times n. And thus we will represent our bits, our 6 high bits and our 6 low bits. So our 6 low bits is represented when select is 0, 1, 0, 0. And as you can see, our output is 0, 0, 1, 0, 0, 0. And then for our high bits, that's represented by 0, 1, 0, 1. And our high bits are all zeros for the high bits of the product of A and B. And then since our low bits and high bits output for select have 2 don't cares, we can go ahead and check them real quick. So 0, 1, 1, 0 is our next combination. And as you can see, it is representative of our 6 low bits, 0, 0, 1, 0, 0, 0. And then for our set of high bits, for 0, 1, 1, we have, once again, we have 0 for our high bits, 0, 0, 0, 0, 0, 0. And now for our next combination of select, we'll go to 1, 0, 0, 0, which is representative of bitwise NOT, and NOT is performed on our A input, and thus our A input is 0, 0, 0, 1, 0, 0, it's 4. So if we knotted that, it would be 1, 1, 1, 0, 1, 1, which we can see here. We have 1, 1, 1, 0, 1, 1 for our LEDs. And then for our next combination of select, this is going to be 1, 0, 0, 1. And that represents A and B. So for A and B, the output R is going to be 0. 0, 0, 0, 0, 0, 0. And then for our next combination of select, we have 1, 0, 1, 0, which is representative of A or B. And A or B is represented by 0, 0, 0, 1, 1, 0. And so our next combination for select is going to be 1, 0, 1, 1. This is representative of A exclusive OR B. A exclusive OR B has the same value as A or B for these two inputs, which is 0, 0, 0, 1, 1, 0. And then for 1, 1, 0, 0, our next select combination, we have a logical shift of A by the bits 2 down to 0 of the entire B vector. So in this case, since A is 4 and B is 2, and this 2 from 2 down to 0 is also 2 within our B, we're basically shifting A by 2 bits. So shifting A by 2 bits, logically, your output should be 0, 1, 0, 0, 0, 0, which is denoted by R. We have 0, 1, 0, 0, 0, 0. And then, since the first least significant bit of our select is a don't care for our logical shifts, we should get the same output if I go from 1100, 1100 to 1101, which is the case. And now we're moving on to a right logical shift. We're shifting A by 2 bits, and we can go ahead and represent that with our select switch as 1110. And as you can see, our output is 0, 0, 0, 0, 0, 1. And now, if we want to shift our A by B bits with sign extended form, or an arithmetic shift, we would use our last set of combinations for these two inputs, which select would be 1, 1, 1, 1, and our output should be 0, 0, 0, 0, 0, 1, which is shown on these LEDs. Okay, so that was our first set of operands. So now I'm going to go ahead and switch the selects back to 0, 0, 0, 0, and I'm going to go ahead and input for A. I'm going to input 1, 1, 0, 0, 0, 1, which is 49 in decimal. And I'm going to input, for B, it's going to be 1, 1, 0, 0, 1, 0, which is 50 in decimal. So if we add the two of those with no carry, we would get 1, 0, 0, 0, 1, 1, which is denoted by these LEDs here. And then for the carry is going to be denoted by 0, 0, 0, 1 for select, which ends up being 1 for output. That's the carry. And then for 0, 0, 1, 0 for select, that represents A minus B, no carry, which is going to be 1, 1, 1, 1, 1, 1, as denoted by these 6 LEDs. And then for the next combination of select, it's 0, 0, 1, 1, and this is the borrow of A minus B, which is 0, denoted by the R output LEDs of 0, 0, 0, 0, 0, 0. And now we can go on to multiplication. So our next combination for the low 6 bits of A times B is 0, 1, 0, 0. And that should be 0, 1, 0, 0, 1, 0. 0, 1, 0, 0, 1, 0. That's what we have for R. And that's our low 6 bits. Our high 6 bits would be the combination of select as 0, 1, 0, 1. these are the high 6 bits, which are 100110. 100110. Perfect. So next is our, since they have 2 don't cares for each of the high and low 6 bits, we'll have a repeat of the last 2. So our low 6 bits are also represented by 0110 for select combination, which gives you 010010. And then for the last high 6 bits, it would be a combination of select 0111, which should produce 100110. And now we have our logical component that we will start using, which is going to start with not A, which is represented by 1000 on select, and our output should be 001110 for not A. And our next combination of select is 1001, 1001, which is A and B, which is represented by 110000. A and B. And then 1010 for select represents A or B, which is represented by 110011. And then for our next and last logical operator, we have A exclusive OR B represented by 1011 for on the select, and it should be represented by 000011, which I see here, 000011. Perfect. And then for our last unit, our last component of our ALU is our shifter. So 1100 is our select combination that represents the left logical shift of A by B, and we should have an output of 000100, which we have. And then for our, since it's a don't care, so both 1100 and 1101 should represent the same output. They're both left logical shifts of A via B. And then our next combination is 1110 for select. This is our right logical shift of A by B bits, where B input is a 6-bit vector, but B sliced 2 down to 0 is the number of bits you use to shift A, which is represented as 001100. And then our last combination, our 16th combination for our shifting component is 1111 for select, and that's a right arithmetic shift, a sign extended, and it should be represented by 111100, as shown by these LEDs up here, 111100. Okay, so our last set of operands are going to be A equal to 111111, and B is also going to be 111111. And thus, for our first select combination of 0000, that's the sum of A plus B without carry, which is going to be 111110. Next is 0001 for select, which is the carry, which is 000001. And then the difference of A minus B is represented by 0010 for our select switches, and this is without a carry, which is just 0, 000000. And then our next combination for select is the borrow of A minus B, which is represented by 0011 for select, and as we can see, the borrow is 1, 000001. And then for our multiplier component, which is represented by first combination 0100 for select, and this is the low 6 bits of A times B, which is 000001. And then the high 6 bits are represented by 0101, which is 111110. And then since there's a don't care in our multiplier, our low 6 bits are also represented by 0110, which is 1 once again. And then our high 6 bits are also represented by 0111, which is 111110. And then for our logical component of our ALU, our first combination is 1000 for our select, and this represents the NOT of A, bitwise NOT of A, which is going to be 000000. And then for our next combination, 1001, this is A and B, which is going to be, let me see here, A and B, 1001. Okay, we're having some technical errors there, but 1001 is going to be represented by 111111. And now A or B is represented by 1010 on our selects, which is 111111. A XOR exclusive OR B is represented by 1011 on the select switches, which is 000000. Our next combination is going to be representative of the component of the shifter component that we have. So 1100 represents A being shifted logically by B due to the fact that B shifts A more bits than A is. You will only have zeros, which is the case here, 000, 000. It's a don't care for the left logical shift of A by B, so 111101 also represents the same function, so we have the same output. And then we have 1110, which represents a right logical shift of A by B bits, which is also all zeros because you're shifting by more bits than there are for A. So we have zeros for our output. And then for our last combination, which is 1111, this is a right sign extended shift of A by B bits. And where B, once again, I just want to clarify this, B is inputted into our ALU as 6 bits, but then we sliced the first 3 bits of B and use that value to shift A, because otherwise the last 2 operands that we've used, last 2 pairs of operands that we've used to perform these shifts would only produce zeros because of the nature of their size. So for our last shift, it's a right sign extended or arithmetic shift of A by B bits, and it is going to be 111111. Thank you.